The future economy based on renewable and sustainable energy sources might utilize battery-powered cars, large-scale solar and wind farms, and energy reserves stored in batteries and chemical fuels. Although there are examples of sustainable energy sources in use already, scientific and engineering breakthroughs will determine the timeline for widespread adoption. One proposed paradigm for shifting away from fossil fuels is the hydrogen economy, in which hydrogen gas powers society's electrical needs. To mass-produce hydrogen gas, some scientists are studying the process of splitting water, 2 hydrogen atoms and 1 oxygen atom, which would result in hydrogen fuel and breathable oxygen gas. Feng Lin, an assistant professor of chemistry in the Virginia Tech College of Science, is focusing on energy storage and conversion research. This work is part of a new study published in the journal Nature Catalysis that solves a key, fundamental barrier in the electrochemical water splitting process, where the Lin Lab demonstrates a new technique to reassemble, revivify, and reuse a catalyst that allows for energy-efficient water split. Chunguang Kuai, a former graduate student of Lin's, is first author of the study with Lin and co-authors chemistry graduate students Zhengrui Xu, Anyang Hu, and Zhijie Yang. The core idea of this study goes back to a subject in general chemistry classes, catalysts. These substances increase the rate of a reaction without being consumed in the chemical process. One way a catalyst increases the reaction rate is by decreasing the amount of energy needed for the reaction to commence. Water may seem basic as a molecule made up of just 3 atoms, but the process of splitting it is quite difficult. But Lin's lab has done so. Even moving 1 electron from a stable atom can be energy-intensive, but this reaction requires the transfer of 4 to oxidize oxygen to produce oxygen gas. In an electrochemical cell, the 4-electron transfer process will make the reaction quite sluggish, and we need to have a higher electrochemical level to make it happen, Lin said. With a higher energy needed to split water, the long-term efficiency and catalyst stability become key challenges. In order to meet that high energy requirement, the Lin Lab introduces a common catalyst called mixed nickel iron hydroxide (MNF) to lower the threshold. Water-splitting reactions with MNF work well, but due to the high reactivity of MNF, it has a short lifespan and the catalytic performance decreases quickly. Lin and his team discovered a new technique that would allow for periodic reassembling to MNF's original state, thus allowing the process of splitting water to continue. The team used fresh water in their experiments, but Lin suggests salt water, the most abundant form of water on Earth, could work as well. MNF has a long history with energy studies. When Thomas Edison tinkered with batteries more than a century ago, he also used the same nickel and iron elements in nickel hydroxide-based batteries. Edison observed the formation of oxygen gas in his nickel hydroxide experiments, which is bad for a battery, but in the case of splitting water, production of oxygen gas is the goal. Scientists have realized for a long time that the addition of iron into the nickel hydroxide lattice is the key for the reactivity enhancement of water splitting. Kuai said. But under the catalytic conditions, the structure of the pre-designed MNF is highly dynamic due to the highly corrosive environment of the electrolytic solution. During Lin's experiments, MNF degrades from a solid form into metal ions in the electrolytic solution, a key limitation to this process. Please support my channel to grow by pressing subscribe button and the bell icon. We will notify you new tech videos. Thank you.